Okay, guys, we're going to start lecture 3 today. Last lecture, we discussed the mathematical models, transfer function, and block diagrams for electrical and mechanical systems. There are some other systems like torsional mechanical systems and systems with gears, and also electromechanical systems that we are going to discuss today. So the simple one is the mechanical systems with gears. So we want to overview the governing equations that we have. According to the continuity, we know that here R1, R1 theta what happened? R1 theta 1 is equal to R2 theta 2. If you have two gears, the input gear, gear 1, and output gear, gear 2, in which they have the radius R1 and R2, and number of teeth on them are N1 and N2. One is by theta 1 and theta 2 shown as the degree of freedom of the rotation, and T1 and T2 are the applied torques. So in this case, we can say R1 over R2 is equal to theta 1, theta 2 over theta 1. And also, we can say that R is proportional to N. So R1 over R2 would be N1 over N2. So we have one relationship here, second relationship here. The third one is that if there is no loss in the system, no friction considered, we can say the power T1 theta 1 is equal to T2 theta 2, which both of them show the work done by the torques for rotation of theta. So these are three relationships that we can use them to simplify mechanical systems when we have gears inside them. Any question? Now, if we go to some examples, if you look at the diagram A, from last session's discussions, we know based on impedance technique that J as it can be written as JS2 and D is like DS and K is like K. So if I want to write the relationship until gear N2, I know that this guy is like JS2 plus D as damping, viscous damping, DS plus K multiplied by theta 2 is equal to the T2 moments. So it is like J theta double dot plus D theta dot plus K theta equal to moment. Now, if I want to write the equation based on theta 1, I can say from the previous slide, T1 theta 1 is equal to T2 theta 2. Therefore, we can write it like JS2 plus DS plus K multiplied by equal to, instead of T2, we can write T1 theta 1 over theta 2, theta 2. And we know that this guy, theta 1 over theta 2 is equal to R2 over R1, or we can say this is N2 over N1. And this guy, theta 2, is like N1 on N2 theta 1. So based on the theta 1 and T1 coordinates, I can rewrite the governing equation as JS2 plus DS plus K N1 square over N2 square theta 1 is equal to T1. So this relationship, the final relationship that we have, shows that if I want to put away these two gears here and write the equations from here, the impedance coming from here to here, I have to write the equation like J N1 to N2 to the power of 2 plus D N1 to N2 S S2 plus K N1 to N2 theta 1 equal to T1. This is going from A to B and coming to C, showing that if you replace the impedances by the number of teeth of destination divided by divided by number of teeth of the, let's say, source to the power of 2 multiplied by the impedance, you will get new impedances. Like instead of J, if you want to put it as theta 1, you have to multiply it by destination N1 divided by source N2. So N1 over N2 to the power of 2 multiplied by J comes here, and D as well, and K as well. This is some method of impedance simplification in gear systems. Clear? Okay. Let's say we have this complicated one. This one is like we have the gears N1 and N2, and we want to find the transfer function theta 2 over T1. This means that I want to keep theta 2, so I want to bring these impedances from here to here. So I can say this impedance becomes J2 S2 plus J1 N2 over N1 to the power of 2S2. So this is the destination to N1. Or D2 becomes D2S plus D1 N2 over N1 to the power of 2S. And K2 becomes K2. That's all. There is no spring in the second hand. So you see that we have the simplified form in this case, like this. So if I want to write in this form, I have to say J2 S2 plus J1 N2 to the power of 2 over N1 N2 over N1 S2 plus D2 S plus D1 N2 over N1 to the power to S plus K2 multiplied by theta 2 is T2. So instead of T2 also we know that it's like T1 N2 over N1. So the transfer function GS that is called theta 2 over T1 is asked would be N1 over N2 N2 over N1, sorry. And you have this part, which is this guy here. Clear? So the transfer function here is the output theta 2 over T1. This is the controlled variable. And this guy is the input or desired output behavior, let's say. Any question?
Sir,
Yeah.
in blue equation, how did the T2 acquired?
So T2 is like here we have this T2 guy. Okay, let me show it on the here. It's like we have this T2 here. Okay. Now I want to write instead of T2 something as T1. So in order to do that, I have to use these relationships. I know that R1 theta 1 is equal to R2 theta 2. So R is related by theta. And R is also proportional to N. So R proportional to N. And also I know these guys. So from here, I can say T1 over T2 is theta 2 over theta 1. And theta is related vice versa or negatively related to R. So this is R1 over R2. And R1 over R2 is related to N1 over N2. Is that the question? Did I
I
answer
mean,
it? Yeah.
shouldn't be the right-hand side of the equation a combination of T1 and T2? Or
No,
T2, does the T2 includes T1 also?
no, they are like free body diagrams. Okay, if you free body diagram these guys separately, okay, you have this force on this guy and some force on this guy. Okay, these two forces are in equilibrium if you consider it like this, T1 and T2. So they are separate on each other. Okay.
Okay, I see now.
Yeah. Okay. So we have this example from previous week's discussion. Again, I want to show that if you use impedance technique, R impedance is R, C impedance is 1 over CS. So the relationship was V2 as output over V1 as input is equal to minus impedance in second hand to impedances in the first hand. So this is guy minus 1 over CS over R, which will result in 1 over RCS. So this is a GS of the system. Or if we have something like this, we know again here we have 1 over CS impedance, here we have R impedance. So V2 over V1 is equal to minus Z2 over Z1, that is R minus R over 1 over CS. That would make minus RCS. This is also the transfer function of this inverting operational amplifier. So last session we discussed these relationships, how we obtain them, but we have now the examples. If you have something like this, some network like this, here we have R2, here we have R1, this guy is 1 over CS. Let me 1 over CS. Okay. So here Z2 that is the output impedance is R2. How about Z1? Z1 can be obtained as 1 over Z1 is 1 over R1 plus 1 over CS. So this would make equal to 1 over R1 plus CS. So V2 equal over V1 is equal to minus Z2, that is R2, over Z1, which is R1 over R1 CS plus 1, and this would make minus R2 R1 CS plus 1 over R1. So in this case also we have these parallel and series cases. Here we have R2 and 1 over C2S. Here we have R1 and 1 over C1S. So this part is like Z2 equal to R2 plus 1 over C2S. And this part is like Z1, which is 1 over Z1 equal to 1 over R1 plus 1 over C1S. And based on these, you can find V2 over V1, the output voltage to the input voltage, as minus Z2 over Z1. So any questions about inverting operational amplifiers? Okay. So I have now here given some examples about grain train and rotational transformers. So we discussed these relationships, like n is the gear ratio if we have. So here it's using the small n value to show all the relationships, but all of them are discussed so far. Regarding the potentiometer, in the first lecture, we discussed their importance as input transducers. So generally here, the whole R is like R1 plus R2, and V2 over V1 is equal to the R2, that is the impedance in the output, to the impedance in the input R. So we have this guy and this relationship. Also, we said that because this is a linear movement here, that is like every theta is increasing the R by some relationship. We can say the R is related to some k theta. The k can be the gain of the system. So the relationship is like if you have r I k theta I and rj k theta j. So you have Ri over Rj always equal to theta j, theta I over theta j. This is the example also we solved at the end of the lecture 1. Next we have rack and pinion. In this case also the important relation that we may use is that the x of the rack is equal to r theta of the pinion. This is also basics that we already know from our previous courses. And there are also some other examples like thermal heating system. If we have some system like with fluid in and fluid out, we have this relationship coming from the thermal conduction inside the heater and the fluid here, in which we have these constants like thermal capacitance, fluid flow rate, specific heat of water, thermal resistance of insulation, and we have the transform of the rate of heat flow heating element Q in the Laplace domain. So this example also I want to show that whether we have any system, we can show it as transfer function of the output to input relationship to model the system as a control system. So it's like generally what we have so far is that we have some governing equations coming from physics, and then we change it into by Laplace transform. We go to the frequency domain and we have the transfer function Gs as output to input relationship, and also we have in time domain like we have the steady state representation, so that we will discuss this next in the upcoming weeks, but this is what we are discussing here, and we are showing with multiple examples that if we have physical system like a thermal system, a mechanical system, an electrical system, we can just find the governing equation based on the physics related to that field, and by Laplace transform and impedance technique change it into the frequency domain representation. And what was the good thing about this? It was the fact that you can change complicated ODEs in time domain into some algebraic equations.